Hey everyone, it's Mr. Wolfe here, and in this video I'm going to be going over scenario 2 in our energy constructing explanations packet. I think it could be helpful to, even if we've done this one in class, just to kind of see the modeling and the thinking through problems like this that might help you out with the others. This also might be helpful if you just weren't in class today on Tuesday. So in this problem, I don't have the actual packet with me, but I kind of drew it out. And I'm going to pull up on my computer the actual problem. So let's see here. The problem says, Mr. Bozade and Mr. Wilkie are at Whole Foods. Mr. Bozade pushes his full cart with a mass of M, so just a general mass from rest, while Mr. Wilkie pushes his empty cart with about 1/3 the mass from rest. After 4 meters for both carts, both carts are going the same velocity. All right. So then the question we're trying to answer is, how do the applied forces compare between Mr. Bozade and Mr. Wilkie? All right. So the first thing we want to do is, even though it kind of like the order is claim, evidence, reasoning, always do your evidence first because you're going to make your claim off your evidence. All right. And honestly, if you don't know, you could always go to the reasoning first or second and then get to the claim if you need to. So let's start with the evidence. So I'm going to look at my initial scenario and ask my question, does my object have a height? Does it have a velocity? It doesn't have a height because it's on the ground. It doesn't have a velocity because the problem says that they start from rest. So in both scenarios, I'm not going to draw anything here. All right. Then it says that at some point they're moving, right? They have a velocity at the end. So I ask myself the same questions. Does it have a height at the end for both of them? No, still on the ground. But I know that they have a velocity. I'm going to do this in pencil because I'm going to change this eventually. All I'm doing now is I know that they are going to have some kinetic energy. I don't know how much yet, so I'm just kind of like in general, all right, I know I need a block there. So if I have a block there, though, right, then I know that if there wasn't an energy in the system initially, that we had to add that energy in, which kind of makes sense because they're pushing the cart. It's because of this applied force that we're adding energy in. Now, all I'm going to do is just say that energy is going to my system. Again, I don't know how much yet because I don't know this value yet. So then if we read the problem, and if we read the problem a little bit more closely, it says that they're going the same velocity. So you might be like, oh, okay, same velocity, same kinetic energy, because that's what it was at the end of first semester, right? But what we've done this semester is we've learned a little bit more about kinetic energy, that velocity is not the only factor that causes or influences kinetic energy. So I might write this up a little bit up here, right? So the equation's not k equals 1/2 v squared, right? Velocity is not the only thing that affects kinetic energy. It's also mass, right? It's also mass. And if we look at the problem, Bose has a mass of m, while Wilkie has 1/3 the mass. So that's going to influence my kinetic energy. Now, you do not have to do proportional reasoning, but just to kind of convince you guys, I'm going to write out this problem with proportional reasoning, and I'm going to say, okay, if I'm doing proportional reasoning, I'm trying to see Bose's kinetic energy, how it compares to Wilkie's kinetic energy. If I'm doing proportional reasoning, I don't worry about my constant 1/2. But Bose has a mass of 1, while Wilkie's is only 1/3 as much. And it says they're going the same velocity afterwards, so I'm going to put in 1, same velocity. So the kinetic energy for Bose is going to be 1 at the end, and the kinetic energy for Wilkie is going to be 1/3. So mass influences kinetic energy, which means that even though I have kinetic energy at the end, I have to draw Bose having more kinetic energy. Maybe I'll do like 3 blocks, and Wilkie having just 1, right? Just because it's 1/3 and 1. Now, actually, I might add one more block because one point I want to hit home is I'm not going to be a huge stickler for like the proportions on this. So if you put 4 in for Bose and 2 in for Wilkie, I'm fine with that, right? Even though it is 1/3 as much, right? I just cared about in general, do you understand that Wilkie has less kinetic energy? Okay. If that's the case, then now I could start to add in my work, right? If there were no blocks before, 2 blocks here, 2 blocks had to go in of energy, right, into my system, and which means there's 4 blocks going to my system in Bose's case. All right. So what I could do now is I could maybe try to answer my claim. I could say, all right, how do the applied forces compare to Bose and Wilkie? And notice that these boxes are not the applied force. This is just the work. This is just the energy that's going into the system. So I can't answer it just directly by looking at my LOL. I'm going to have to do a little bit more things. So I'm going to hold off on the claim right now, and I'm going to get to the reasoning. Maybe that'll help me out. Right? Especially this first question. What energy do we need to focus on? That's kind of my simplified way of saying that first bullet point. Right? So what I'm going to say, and maybe I will do this a little bit color coding, make this red, and if I'm trying to answer force, so because, or I might, you know what, I'm going to try to write this as simple as possible. Right? Looking, right, for force, so need to look at work. So all I'm saying that, and by the way, how I know that is if I write down all my equations, right? K equals 1/2 mv squared, UG is equal to mgh, work is equal to force times distance. This is the only equation, right, that has force in it. Right? And remember, my LOL just tells me my energies, so I'm either going to only be able to look at kinetic energy potential or work here. Right, so now I'm looking for force, so I need to look at work. So in order to solve this problem at the end of the day, I'm going to look here. But first I need to say how I know that there's more work that Bose is doing compared to Wilke. So the next thing I'm going to do is I'm going to just talk about my LOL diagrams, how that leads me to my claim. And my recommendation is to start with your first L. Right? So I might say something like, all right, if I look at these first L's, no velocity or height, so no energy. And by the way, if you guys want to write your explanations like this, I'm okay with it. You don't need to have to be super wordy or anything. Okay. And then, you know, you could go in order. You could talk about this, the second O and then the third, but that's not always the best case. All right. You do the first O, you do the L. You'll decide to do the second L first or second, or the circle second, based on if it's logic or not. And I know I didn't do the best job at just explaining that right there, so let me give you an example. All right? It makes sense to answer this one second, right? Because that's going to give us our answer for this one. So I'm going to say if I look at my second L, let's say Bose plus Wilke have same velocity, but Bose has more mass. Just M, I could put in. So he has more K. Now, if this is still like a something that you're kind of, it's trouble wrapping your head around, I mean, I know I could show you the equation. I could say, look at, you increase the mass, and that's going to influence kinetic energy. But I think at this point, you guys have so much ingrained, like velocity is kinetic energy. And velocity is not kinetic energy, it just influences it. So a good way to explain that is, and I did this in class today, is if I were to maybe, like in class, toss you a golf ball, right, at like from 3 feet away, and I could toss that golf ball, and then I could also take a bowling ball, and I could toss that to you at about the same velocity. Right? In terms of which one would you rather catch with one hand, you'd rather catch the golf ball, right? Because even though they're going at the same speed, that bowling ball, because it just has much more mass, has so much more energy for you to stop, right, with one hand. Right? So hopefully that helps with that. So Bose and Wilke have the same velocity, but Bose has more mass, so he has more K. Right? Right? This means, so now because I know this information about the second L, now I could figure out what's going on here. This means that he needed to do more work compared to Wilke. Something along the lines of that. Hopefully you guys can still see that. So at this point, I've described my LOL diagrams, but I'm actually not done yet. That's why sometimes we'll put that, hey, make sure to write a concluding statement here, right? Because the question I'm trying to ask is not how much more work is Bose doing, it's how do their applied forces compare, right? So that's when it gets to a little bit more of kind of like that proportion reasoning. And I have a slide on the Google Slides that kind of just encompasses everything. But what I could do is I could say, and maybe I'll draw this up here because it's by Wilke and Bose, is I could say, all right, well, the thing that I know is the same in both of these, is the same in both these scenarios is the distance. All right, so maybe I'll put in, maybe I'll write this right here, D. I'm going to box it in just to kind of highlight that this variable is not changing. All right. Now I know from my LOL diagram, and this is why the LOL diagram is helpful, is that Wilkie has less work compared to Bose. Right, so then the question is, well, what would that force have to be, right, in order for Bose to have more work? Well, since these are on opposite sides of the equal sign, they're directly related, which means that this force would have to be bigger. Because the distance is the same, this force would have to be bigger in order for Bose to have more work. Or in other words, because Bose has more work and the distance is the same, he would have to give, right, a larger force. So by the way, if you ever want to write that in your reasoning, the W equals F times D and the size of the letters to help you with your reasoning, I'm fine with that. And honestly, I think it helps a lot. So for a concluding statement, I could say, because they both travel same distance, but Bose does more work. He has to exert a greater applied force. And now we've answered the claim. All right, now we're kind of going to Bose exerts that greater applied force right there. So I know that it's a little lengthy. Hopefully, doing multiple examples helps. Hopefully, this example helps. I know I kind of went into a lot of detail, but I kind of wanted to make sure that you kind of get every single part of the thinking that goes into this. So thanks for watching, and I'll see you guys on Thursday or possibly Friday.